Hello, welcome back to MEC 416/816 Engineering Acoustics. In this video, we're going to go through a discussion of what the energy density is associated with acoustic waves. So the energy transported by acoustic waves through a fluid consists of two parts. The first is that of the kinetic energy that is caused by the motion of the particles themselves. And then the second is the potential energy due to the compression or the expansion of the fluid itself. To this end, we're going to consider a small fluid element that is moving with the fluid, and we're going to assume that it occupies a volume V0 of that undisturbed fluid. The mass of that element is then rho 0 times V0, and we can write that its kinetic energy is going to be E sub k, representing the kinetic energy, is 1/2 times rho 0, the density, times the volume, V0, times U dot U, where this is the fluid particle velocity, or in other words, 1/2 rho 0 times V0 times the quantity U1 squared plus U2 squared plus U3 squared, which we could write out as being equivalent to 1/2 rho 0 times big V0 times U, where U is just a scalar amplitude. Okay, so then the potential energy associated with the volume V0 to a new volume V is going to be written as E sub P is equal to the minus the integral from starting at V0 to our new volume V times of P, the acoustic pressure, times dV. Here the negative sign implies that a compression increases the potential energy, and that means that there's work being done on the fluid element. So by compressing that fluid element, we are storing energy in it, whereas by expanding it, we are releasing energy. Okay, so from there, we can apply conservation of mass, meaning that there's no mass added or created during this expansion process. And from there, we can write that dV is equal to minus V over rho. Let me rewrite that. V over rho times d rho. Okay, and since dP over d rho is equal to c squared, we can find that dV is then going to be equal to the quantity V over rho c squared, and that quantity then multiplied by dP. From there, if we substitute equation 51 into equation 49, and I'll scroll up so you can see what equation 49 was again, we substitute those in, we will find that the potential energy, or EP, is equal to 1/2 times the fraction P squared V0 divided by rho 0 C squared. And then the total acoustic energy is going to be equal to E is equal to the kinetic energy, EK, plus the potential energy, which will be equal to 1/2 times rho 0 times V0 times the quantity U squared, that's that amplitude squared, plus the quantity P divided by rho 0 C, that quantity squared. And that is our total acoustic energy. So then the instantaneous energy density can be written as, we're going to use the script E as being equal to E divided by V0, and this has units of joules per cubic meter. So the script E, with the I being instantaneous, is now a function of time, is equal to 1/2 rho 0 times the quantity U squared plus the quantity P over rho 0 C quantity squared. And that's our instantaneous energy density. Instantaneous energy density. Okay, so then we find the energy density by taking a temporal average of that instantaneous energy density, and then we'll find that the energy density is equal to the temporal average of the instantaneous energy with respect to some period, or 1 over big T, where big T here is that period, from 0 to that period, EI dt. And that then is our energy density. Okay, in the next video we're gonna talk about the acoustic intensity. Thank you.